Okay, in this video we are going to do a lot of series convergence problems, like 30 something of them, I think. So what I'm going to do is I'm going to assume that you already know basically all of the tests. So here's the list. So geometric, p-series, telescoping, nth term test, integral, direct comparison, limit comparison, ratio, root, alternating series test, and absolute convergence. I didn't look at the problems ahead of time, but I'm probably going to use the limit comparison, nth term test, integral test, and probably the ratio test a lot. And I'll probably have to use the alternating series test, but if I can, I'll just check for absolute convergence. So that's kind of like mentally going into it, what I'm thinking I'll end up doing. I might do direct comparison just to like do it if it comes up. Let's get started. So we're going to do a lot of problems here. So I'll have in the description, I'll have timestamps, I guess, for each of the problems. I hope you find this helpful in the long run because it's probably going to be a really long video. So let's see. All right. So here we're doing the sum from 1 to infinity of n squared minus 1 over n squared plus n. So the first thing you should ever think of is like, what's the limit of this thing? And in this particular case, if I take the limit as n approaches infinity of the nth term, I'm definitely going to get 1. So you might use L'Hopital's rule on this. It depends on what kind of work you're required to show. But this is a quadratic over a quadratic, so the limit's the ratio of the coefficients, which in this case is 1 over 1. So that's 1. And then I'm not going to make you watch me write out this whole thing, but this is what I would write. Therefore, the sum from 1 to infinity of n squared minus 1 over n squared plus n diverges by the nth term test. So make sure you're always thinking, is the limit actually equal to 0? Because if it's not 0, we definitely know this thing doesn't converge. All right, let's take a look at another one that looks an awful lot like this, but is slightly different. So we have the sum from 1 to infinity of n minus 1 over n squared plus n. Okay, so this one, if I like in my head take the limit, I'm going to get 0. So I can't just use the nth term test again. But when you do problems like this kind of looks like just a p-series where people started like adding things or subtracting things. So what I usually do is look at the dominant term. So I'm thinking in the numerator, the dominant term is just n, and in the denominator, the dominant term is n squared. So I'm just going to look at what this does in comparison to n over n squared, but n over n squared is just 1 over n. So I'm going to try the limit comparison test and see what happens. So limit as n approaches infinity, the nth term of the series that I'm interested in divided by the nth term of the series I'm comparing it to. And then this we can simplify to this. And then this limit is definitely 1. So usually when you do this, you like kind of know the result. You're just showing the work. So that's what's happening here. Like as soon as I knew that this looked like 1 over n, I knew that it definitely diverges. But now I'm trying to like prove it to whoever's reading this. So I take that limit, I get 1. That's a positive finite value, which is what we're looking for with the limit comparison test. And that means that both of them do the same thing. So I'm just going to write it up. So we'll say since the sum from 1 to infinity of 1 over n diverges because it's harmonic, we know that the sum from 1 to infinity of n minus 1 over n squared plus n diverges by the limit comparison test. All right. Okay, now we're going to look at the sum from 1 to infinity of 1 over n squared plus n. So I look at that, and that again just looks like something like a p-series where somebody decided to add n in the denominator. So I immediately think that I should just compare this to 1 over n squared. So my instinct here is to just use limit comparison. If you do the ratio, take the limit, you're going to get 1, therefore they do the same thing, so you know that it converges. But since in this case we can do direct comparison and we should at least practice it, I'm going to do that instead. So I like to start off comparing the denominators. So n squared plus n is bigger than n squared, which is good because I'm trying to show convergence. So I need this to start out bigger so the reciprocal will be smaller. But this implies that the reciprocal is smaller, which means if I add up all the terms, I know that the sum of all these terms is going to be less than the sum of all these terms, and now I'm ready to say that this thing converges. So I'm just going to write it out, and then I'll read it. So since the sum of 1 over n squared converges, it's a p-series where p equals 2, and if p is greater than 1, it converges. We know that the sum of 1 over n squared plus 1 converges by direct comparison. So that's a good example of using direct comparison. But if the problem says if you can find the sum, find the sum, we want to do this problem a slightly different way. So I'm going to redo the problem. So this, if you notice, you can factor that denominator into 1 over n times n plus 1. And that is a classic partial fraction situation. So I'm going to set that up. So I have a over n plus b over n plus 1 is equal to 1 over n times n plus 1. And now what I'm going to do is I'm going to use kind of a cover-up method. So if n is equal to 0, then that means that a is going to be 1. If n is negative 1, it means b is going to be negative 1. And if you're not sure about the cover-up method, there are definitely videos about that you can search for and find. So I'm going to rewrite the series here as the sum of 1 over n minus 1 over n plus 1. Now what I'm going to do, I always do this with telescoping. I look at the partial sums and see if I can find a formula for the partial sum. So s sub k, so the kth partial sum, is going to be the sum from 1 to k instead of 1 to infinity of 1 over n minus 1 over n plus 1. And what I usually do is just list out a couple of the terms. So I'm plugging in 1, then I'm plugging in 2, then I'm plugging in 3, and I kind of get what's going on at this point, so I'm just going to jump to the end here. And you can see that like everything in the middle is going to cancel out, so you have that minus 1/2 plus 1/2, minus 1/3 plus 1/3. So if you stop at the kth term, all that's going to be left is the first term, 1, which never canceled with anything, and then the last term, which is minus 1 over k plus 1. So s sub k, so that's a formula for the partial sums, and if you think about how series work, when you originally talk about them, you talk about the value of a series being the limit of the partial sums. So if I take the limit of the partial sums here, to get this, that's definitely 1 because 1 over k plus 1 goes to 0, which means that not only does the series converge, but it converges to 1. So we can say this thing equals 1. All right. Okay, new problem. So this is number 4. We're going to go from 1 to infinity of negative 1 to the n plus 1 times n minus 1 all over n squared plus n. Okay. So if you think you recognize this, it's because you kind of do. It's problem number 2, but now it alternates. So we already found that problem number 2 diverges. So the first thing I would note here is that this does not converge absolutely, which just means throw absolute values around it and see what happens. And we already did the work in number 2. So it doesn't converge absolutely, so now I'm thinking I probably have to do the alternating series test. So depending on how much work you need to show, I worked out the derivative here. So if f of x is x minus 1 over x squared plus x, then f prime is the negative of the quantity x squared minus 2x minus 1 over the quantity x squared plus x squared. So that's quotient rule and some simplifying. And then that means that f prime is less than 0 for x greater than 1 plus root 2. So that means that this thing is decreasing when x is greater than 1 plus root 2. But we only really want integers. So I'm going to say, therefore, when x is greater than or equal to 3. So I've done the work to show that this will be decreasing, that f of x will be decreasing. Now I need the limit. So the limit as n approaches infinity of n minus 1 over n squared plus n. So you kind of disregard the alternating part there, and you're just looking at the limit of the magnitude of the terms. And this limit is definitely 0 because it's linear over quadratic, or you could use L'Hopital's if you want. And now I'm ready to write up my answer. So I'm going to say, since, so here I'm going to go from 3 to infinity, because that's what I need for decreasing. So it has terms that alternate, and then we did the work to show that they decrease in absolute value, right? So they decrease. And we also found that the limit of the nth term is 0. So those are the three criteria for convergence by the alternating series test. So we can say that the sum from 3 to infinity definitely converges by alternating series test. And then just to go back, if I add in two more finite terms, it's definitely still going to converge. So I'm going to say, therefore, that original series also converges. So we did the work from 3 to infinity, which is kind of weird, but that's where it was decreasing, and that's one of the requirements. And then you can just add in however many finite terms you need. All right, so that's that problem. All right, new problem. Let's see. So this is number 5. We're going to go from 1 to infinity of the quantity -3 to the n plus 1 over 2 to the 3n. So you might initially look at this and be like, oh, geometric ratio is like 3/2, so diverges. But you should probably work on it a little bit because that 3n is a little different, right? So first thing I'm going to do is peel apart that numerator and make it -3 times the quantity -3 to the n. Now I'm going to deal with that 2 to the 3n. So over here, 2 to the 3n is 2 cubed to the n, which is 2 cubed is 8, so it's 8 to the n. So we've actually rewritten this as this, and now it's pretty clear that the ratio is not actually 3/2, it's actually -3/8. So let's finish rewriting this. And since it's geometric, as soon as you get that the ratio is -3/8, you know this thing converges. So if the question is just, does it converge, we could definitely write down that this original thing converges because it's geometric with r equals -3/8, and that means the absolute value of r is less than 1. But if you're supposed to find the sum when it converges, if possible, we should do that. So I'm going to start with this, which we rewrote as this thing. You don't really need to do this as long as you know what r is, but I think it's a good idea. So the sum of this is going to be the first term, so you take n equals 1 and you substitute it in, and that gives you -3 times -3 is 9 over 8. And then over 1 minus the ratio, so 1 minus -3/8. And if we simplify this, we end up with 9 over 11. Okay, let's take a look at another problem. So we want to do the sum from 1 to infinity of 1 over n plus n cosine squared of n. So this is a little weird. It's always strange when you mix in cosines and sines, but they have a really nice property, especially if you're squaring them, that they're between 0 and 1, which means that we're just multiplying that second n there by a number between 0 and 1, which means we can make a nice inequality out of this. So we know that n plus n cosine squared of n is definitely less than or equal to n plus n, which is just equal to 2n. So we have a relationship that's going to work for us potentially, provided we end up in kind of the right direction. So I'm going to take the reciprocals here to kind of get back to the series. And this is good because 1 over n plus n cosine squared of n is greater than or equal to 1 over 2n. 1 over 2n, if we sum it up, let's sum these things up. 1 over 2n, if we sum it up, is just the harmonic series. Well, half of the harmonic series, but diverges still. So we actually know this diverges. This is another direct comparison thing. So I'm going to say, since the sum of 1 over 2n, which is 1/2 the sum of 1 over n, diverges, and I like to give a reason, so it's harmonic, or you could say p is equal to 1, we know that this other series diverges, diverges, I forgot that word, diverges by direct comparison. Okay, so that's another direct comparison problem that we can do. Okay, new problem. We want to do the sum from 2 to infinity of 1 over n root natural log of n. So things that have natural log of n in the denominator and an n in the denominator tend to be integral test problems, so I'm going to try the integral test on this. So f of x, basically just turn all your n's into x's, will be this. Okay, so this function has a problem at what? At 1 and at 0, but we don't have to care about that because we're starting at 2. So we definitely have a continuous function. we're always dividing by 1 by a positive number, so we're definitely a positive function. And the top is a constant, or the numerator is constant, and the denominator is growing, so definitely decreasing. So now what we do is we take a look at the improper integral, where notation matters. All right, so I rewrote the function a little bit, so it's a little clearer what's going on here. I'm going to let u equal the natural log of x, so then du would be 1 over x dx. So this is just the integral of u to the negative 1/2. So that's plus 1, so it's u to the 1/2, and then times 2. So I'm going to just write the limit as b approaches infinity of 2 root natural log of x from 2 to b. And then I'm going to use, so I'm going to substitute b, and I'm going to substitute 2 to get this. But natural log of b goes to infinity as b goes to infinity, so this actually just diverges. So I'm going to say this is infinity. And then I'm just going to write out the kind of long answer. So we had to do all that work, but what I'm going to say is, since f of x is continuous, positive, and decreasing, and the improper integral diverges, we know that the series also diverges by the integral test. Okay, new problem. So problem number 8, we're going to go from, I guess that should be k equals 1 to infinity. Maybe that is a k. I don't know. K equals 1 to infinity of 2 to the k times k factorial over k plus 2 factorial. So I see a lot of factorials, so I'm going to use the ratio test. So I'm going to calculate rho is limit as n, that should be a k. Man, I just use n all the time with these things, so it's like hard to get it out of my head. But that should be k approaches infinity of, so it's a k plus first term, so you take every k you see and replace it with k plus 1. So it'll be 2 to the k plus 1, k plus 1 factorial, and then k plus 1 plus 2 is k plus 3 factorial. And then I'm going to multiply by the reciprocal of the original. Really, I'm doing the n plus first, or the k plus first, divided by the kth. But since you do it all the time, I typically just multiply by the reciprocal. So I'm going to multiply by k plus 2 factorial over 2 to the k times k factorial. Now what I'm going to do is go through and simplify similar things. So k is going to infinity. 2 to the k plus 1 over 2 to the k is just 2. K plus 1 factorial over k factorial. So you make k plus 1 factorial into k plus 1 times k factorial. So we just are left with k plus 1. And then we do the same sort of thing for k plus 2 factorial and k plus 3 factorial, which will just leave us with k plus 3 in the denominator. And if we take that limit, we definitely get 2, which is bigger than 1. And we can say, therefore, our summation diverges by the ratio test. All right, after I finished that, I realized, I got a little excited about the factorials, and I just decided to go with the ratio test. A better thing to do would realize that there are factorials in the numerator and denominator, so maybe I should just simplify that. So a different approach is to rewrite this thing as just 2 to the k over k plus 2 times k plus 1, and then take a look at the limit to infinity, as k approaches infinity, of the nth or the kth term. I guess now we're using the kth term test, but this limit is definitely infinite. You could use L'Hopital's rule twice, I think, or you can just look at it and say an exponential grows faster. Therefore, we can say, or could have said, that this diverges by the nth term test right away and not have used the ratio test. So I saw factorials and I went for the ratio test, but I could have done it faster with the nth term test. Always look for the nth term test. Okay, new problem. Let's see. So we want to go from 1 to infinity of n squared e to the negative n. So I really feel like this is meant to be done with the integral test when you look at it, but I'm actually going to use the ratio test, which frequently works with if you have something to the nth power. So I'm going to use the ratio test instead because it's a little easier. This would require integration by parts, and I don't really want to do that. So I'm going to calculate rho, which is the limit as n approaches infinity of the absolute value of n plus first term. So that's going to be the quantity n plus 1 squared over e to the n plus 1, and then times e to the n over n squared. And then if you kind of do the cancel thing, so you have e to the n over e to the n plus 1. So I'm going to drop the absolute values here because we're going to infinity and there's no negatives involved. We just have n plus 1 squared over e to the what do we have? The quantity n plus 1 squared over e times n squared. If you go to infinity, that's just basically n squared over n squared is 1, so we end up with 1 over e, and 1 over e is less than 1, and so we can say that this thing converges by the ratio test. So as I mentioned at the outset, I feel like this is supposed to be an integral test problem, and if you use the integral test, it'll definitely work. You get a convergent improper integral, but you have to like show that that thing is decreasing, and you have to use integration by parts, and so that seemed like a lot more work. So I just went with the ratio test. Let's take a look at another one where we actually will use the integral test. So this one looks really similar. We're going to go from 1 to infinity of n squared e to the negative n cubed. I look at that function, n squared e to the negative n cubed, and I think that's definitely meant to be integrated. So I'm going to immediately write down that f of x is that thing, but with x's. And now I'm going to do the improper integral. So I'm being a little sloppy on this. I really need to show that this thing is decreasing, continuous, and positive. It's definitely continuous, definitely positive. And if you do the work, you'll see it is decreasing for x greater than or equal to 1. It's like 0.89 or something. But I'm just going to do the improper integral here because we're doing a million problems, and I don't want to show every step on every one of them. So this, if I integrate it and use proper notation, so it'll be the limit as b approaches infinity. I get negative 1/3 e to the negative x cubed from 1 to b. So that was where I typically just let u equal e to the negative x cubed, and then I just end up integrating like du, well, negative 1/3 du in this case. But you can do that however you like. You could let u equal negative x cubed and go from there. And if I evaluate this at b, and I'm going to evaluate it also at 1, I get this. And so if b goes to infinity, that first part definitely goes to 0, so we get this. And so now I can just write this up and say that f of x is continuous, positive, and decreasing, and the improper integral converges. Therefore, the series will converge by the integral test. So that was one problem that I think you were supposed to use the integral test on, but I used the ratio test. And then another one where it looked very set up for the integral test, and I went for it. You also could use the ratio test on this one if you'd like. It would have worked just as well. Okay, let's take a look at a new problem. So let's say we want to do the sum from 2 to infinity of negative 1 to the n plus 1 over n natural log of n. So this one, if you know the alternating series test, might be the simplest problem that we've done so far. So I'm just going to say that this series has terms that alternate. They definitely decrease in absolute value because the numerator is a constant and the denominator is growing. And the limit as n approaches infinity of 1 over n natural log of n is definitely 0. And therefore, we can say that this series converges by alternating series test. That's like a classic example of the alternating series test. Let's look at a less classic example. So we have this. This one is maybe a little more complicated, so we're going from 1 to infinity, negative 1 to the n, so definitely alternating, n over n squared plus 25, so that might be a problem. So what I'm going to do here is, I want to use the alternating series test, but I'm going to take the derivative of this function, so I took the absolute value, and then I change all the n's to x's. The derivative of this works out to negative quantity x squared minus 25 over x squared plus 25 squared. And if we set that less than 0 and solve, we find that f prime is less than 0 when x is greater than 5. So instead of looking at the series that I was given, I'm going to look at the series from 6 to infinity. And from 6 to infinity, this justification is just as easy as problem number 11 was. So I'm going to say it has terms that alternate, decrease in absolute value, and the limit as n approaches infinity of n over n squared plus 25 is 0. So that means that I know that the sum from 6 to infinity of this alternating series definitely converges by the alternating series test. Since I left out the first, second, third, fourth, and fifth terms, but those are finite numbers, I can say since I know from 6 to infinity converges, I also know that the original series converges. So this is like a thing that you have to do sometimes because of the criteria that the terms decrease. So taking the derivative can help you see where a function is decreasing, and it just kind of depends on how much work you have to show. So I use a calculator to find the derivative and solve for less than 0. Okay. All right, let's take a look at another problem. So we're going to go from 1 to infinity of 3 to the n squared over n factorial. So this feels like a ratio test problem, so I'm just going to jump in and do that. So it's the limit as n approaches infinity of the n plus first term, so it'll be 3 to the n plus 1 quantity n plus 1 squared over quantity n plus 1 factorial, and then times the reciprocal of the original, which is n factorial over 3 to the n times n squared. And then if you look through for things you can kind of simplify, so 3 to the n plus 1 over 3 to the n is just 3. And then the n plus 1 squared is going to stay. And then n factorial over n plus 1 factorial is just 1 over n plus 1 because you peel off the n plus 1. So that, and then n squared is still there. And then you look at this and you have a quadratic over a cubic if you were to expand everything, so you definitely get a limit of 0. Or you could use L'Hopital's rule, or however you want to deal with that. You could expand it and divide through by the highest power of n in the denominator. Whatever you want to do. I want to just look at it and say that limit is 0. That is definitely less than 1, and therefore we can say that the series converges by the ratio test. All right, let's take a look at another problem. So it's the sum from 1 to infinity of just sine of n. So this one, I'm just going to look at the limit of the nth term. So sine never really settles down. So the limit as n approaches infinity of sine of n just doesn't exist, so it does not exist. And if that's the case, then we already know what's happening here. So we didn't get a limit of 0, so the sum of sine of n diverges by the nth term test. Let's look at another one. So here we have the sum from 0 to infinity of n factorial over this weird product. So 2 times 5 times 8 times blah, 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 all the way up to 3n plus 2. Okay, so there's a factorial, so I'm going to try the ratio test. So that'll be the limit as n approaches infinity of the n plus first term. So it's n plus 1 factorial over 2 times 5 times 8 times, if I let n, so if it's n plus 1, it's 3 times n plus 1 plus 2. So 3n plus 3 plus 2 gives me 3n plus 5. And then times the reciprocal of the original. So we have this. I feel like the real challenge here is to not be intimidated by that weird product in the denominator, because we can definitely deal with it. So let's simplify. So it'll be the limit as n approaches infinity of, so n plus 1 factorial over n factorial just leaves us with n plus 1. And now I need to figure out what to do. So if you look at the denominator, it's of the original, 2 times 5 times 8. So it keeps increasing by 3. So it would be 2 times 5 times 8 times 11, because I just keep adding 3. So what I'm going to do is I'm going to think about what term would be immediately before 3n plus 5. Well, I would just subtract 3, right? And that would take me to 3n plus 2. So really the denominator is 2, 5, 8, and then 3n plus 2, and then that is being multiplied by 3n plus 5. So if we expand it like that, you can see that the whole thing is going to simplify with the other numerator and just leave us with 3n plus 5. And if we take that limit to infinity, we get 1/3, and 1/3 is less than 1. And so we can say the original series converges by the ratio test. So don't get afraid of those kinds of products. You can always deal with them somehow related to what we did. Think about what the prior term would have been and work from there. All right, let's see. Okay, new problem. So we want to do the sum from 1 to infinity of n squared plus 1 over n cubed plus 1. So this looks familiar. It looks kind of like maybe just n squared over n cubed, but n squared over n cubed looks an awful lot like, or is identical to, 1 over n. So when it looks kind of like a p-series that's been messed with, or if I can just consider the dominant terms in the numerator or the denominator, that's what I'm going to do. So in this case, I'm going to limit compare these two series. So I take the nth term of the first series, divide it by the nth term of the series that I know diverges, and I'm going to simplify the limit. So I get this, and then that limit is definitely 1. And so since I got a positive finite value, I know that they both do the same thing, so I'm just going to write up my answer. So since 1 over n diverges, it's the harmonic series. I know that the given series diverges by the limit comparison test. So that one should feel pretty straightforward if you've gone and done every one of these problems so far, which I'd be amazed if anyone has done, but hopefully someone has. Let's take a look at another one. We're going to go from 1 to infinity of negative 1 to the n, so this is alternating, negative 1 to the n times 2 to the 1 over n. Okay, so 2 to the 1 over n, we want to think what happens as we go to infinity with that thing, because it doesn't feel like it's going to go to 0. So if I think about it, it's 2 to the 1 over n, so that's like 2. What happens to 1 over n as we go to infinity? So 1 over n goes to 0, so it's really like 2 to the 0, which is 1. Okay, so that part has a limit of 1, which means that the limit as n approaches infinity of negative 1 to the n times 2 to the 1 over n just kind of like eventually is going back and forth between positive 1, negative 1, positive 1, negative 1. The limit just doesn't exist. So it's definitely not 0. And if the limit doesn't exist, we can say that the series diverges by the nth term test. So we need the limit to be equal to 0 if we're going to possibly converge. So since the limit doesn't exist, there's no way that it can converge. All right, let's look at another one. So the sum from 2 to infinity, so we're not starting at 0, we're not starting at 1, we're starting at 2 because of that denominator there. So 2 to infinity of negative 1 to the n plus 1 over radical n minus 1. This is like a classic alternating series, so I'm just going to write it down. This definitely converges. So we need alternating. We need terms that decrease in absolute value. So the numerator is a constant and the denominator is growing. So we know that this decreases. And we need the limit to be 0, but this definitely goes to 0, right? Because the numerator is constant and the denominator increases. So if we can say those 3 things, then we can say that the series converges by the alternating series test. So that one was very straightforward, and that was nice. Because the next one is less straightforward, which kind of keeps happening. So we're going from 1 to infinity of negative 1 to the n, so it's alternating again, natural log of n over radical n. So I'm a little worried about this one decreasing, so I'm actually going to look at the function. F of x is natural log of x over square root of x. That should be square root of x. Did I do the whole problem wrong? Let me just check my... No, I did it right. Okay, so that should just be the square root of x. That's just... I wrote that wrong. That should be square root of x. This gives us a derivative. The correct function gives the derivative 2 minus the natural log of x over 2x to the 3 halves. And then that derivative is less than 0 whenever x is greater than e squared. And that means, so e squared is 7 point something. So that means definitely when x is greater than or equal to 8, because we really worry about integers with these problems. So what I'm going to do is alternating series test from 8 to infinity. And then if it converges from 8 to infinity, then when you add the 7 original terms, it's still going to converge. So let's see. So I'm just going to write it down. The sum from 8 to infinity does converge by the alternating series test because it alternates, its terms decrease in absolute value, and the limit as n approaches infinity of the natural log of n over radical n is 0. So we know that that converges by the alternating series test. The hardest part is showing that this thing's decreasing anywhere. And then if that converges, then we can say that the original converges as well because we just have to add in the 7 terms that we kind of skipped. Okay, so that's 2 alternating series problems. Okay, new problem. We're going to go from 1 to infinity of n plus 5 over 5 to the n. So My initial impulse on this I will share after doing the problem, but I'm actually going to do the ratio test on it because I think it's going to make the answer drop out pretty quickly. So we're going to do the n plus first term. So it's the limit as n approaches infinity. The n plus first term, n plus 1 plus 5 is n plus 6 over 5 to the n plus 1 times the reciprocal of the original. So we get this, and then this, you can kind of like simplify the 5 to the n and the 5 to the n plus 1. So we're just left with n plus 6 over 5 times the quantity n plus 5. And then if we go to infinity, we get 1/5, and 1/5 is less than 1. And so we can write our answer. So we definitely know this thing converges. So that converges by the ratio test. My initial instinct was to actually split this up into two different series. I was going to use the integral test on the first one. I was going to look at the second one and say that's geometric. And then I was going to sum up two convergent series. That was going to take forever, so I'm glad I decided not to do that. But it would have worked. All right, so let's do another one. So here we have the sum from 1 to infinity of the quantity -2 to the 2n over n to the n. So that n to the n makes me a little nervous about using the ratio test. Like, we could probably work our way through it, but it's probably going to be weird. So instead of doing that, I'm going to consider simplifying this thing. So let's see. And use the root test on it. So I'm going to actually use the root test. This is the first time we did 20 problems and we finally showed up one that the root test is probably more useful on. So the quantity -2 to the 2n is the quantity -2 squared and then to the n, and the quantity -2 squared is 4. So it's really 4 to the n over n to the n, which we can make 4 over n to the n, and now it's like perfect for the root test. So I want to take the limit as n approaches infinity of, it's the absolute value of the nth term to the 1 over n, but 4 over n is always positive. So this is just going to be the limit as n approaches infinity of 4 over n. That definitely goes to 0. 0 is definitely less than 1. And so we can say this thing converges by the root test. So don't forget about the root test. The root test usually, when you're looking at a problem and you're thinking like, man, I don't want to use the ratio test on that, that's almost always a great candidate for using the root test. Let's take a look at another problem. We're going to go from 1 to infinity, radical n squared minus 1 over n cubed plus 2n squared plus 5. I look at this as like a p-series problem that just has like a lot of noise in it. So what I'm going to do is I'm going to take out the noise, right? So ignore that minus 1, ignore that 2n squared plus 5, because if you go to infinity, those terms aren't really contributing much. It's really the radical n squared in the numerator and the n cubed in the denominator that are like doing all the work. And then this, because we're dealing with positives, is the same as just n over n cubed, which is the same as 1 over n squared. All right, so now we're going to do a limit comparison. So it's a limit of, so the nth term of the original over the nth term of the series that we chose. And then this, I'm just going to simplify a little bit. Basically, with the way that we construct our series, we pretty much always get 1 when we do the limit comparison test, which is totally fine. I mean, we need a positive finite value, and we're going to get that. And so now I'm just going to write up this thing. So 1 over n squared I know converges because it's p-series. So since the sum of 1 over n squared converges with p equals 2, we know that the given series converges by the limit comparison test. All right, let's take a look at another problem. So it's the sum from 1 to infinity of the tangent of 1 over n. So in my head I first think like maybe the limit's not 0, but 1 over n is going to 0 as n goes to infinity, and the tangent of 0 is 0. So the nth term test isn't going to help us here. But looking at it, that 1 over n might help. So I'm going to try limit comparing it to just the sum of 1 over n. So this is a really common thing when you have a trig function with some kind of function in the argument. Like, try comparing it to that function that is the argument. So here it's 1 over n. Let's do a limit comparison. Then, of course, we have to hope that it works, but it usually does. This, okay, so if we go to infinity, we get the tangent of 0, which is 0, over 1 over infinity is 0. So we can use L'Hopital's on this. So it's the derivative of the top. Derivative tangent is secant squared, and then we got to chain rule this thing, and then divided by the derivative of 1 over n. So it's actually the chain rule part that makes this work most of the time, because the chain rule part from the numerator will just cancel with the derivative of the denominator. And then we just have to see if this gives us something positive and finite. So the secant of 0, so the cosine of 0 is 1, so the secant of 0 is 1. So this limit is 1. And then we can just write up our solution. So same thing, where we are, what are we even doing? Oh, limit comparison test. Okay, so they both do the same thing. I got confused there. I thought I was doing the ratio test. So since 1 over n diverges, I know that this series, the tangent of 1 over n, will also diverge, and that is by the limit comparison test. Okay, so 2 different limit comparison tests. The one with the trig thing is a little weird. I do recommend you always just try to compare it to whatever the argument is. It's usually like 1 over n squared, something like that. Okay. All right, let's take a look at this problem. So we have the sum from 1 to infinity of the cosine of n over 2 over n squared plus 4n. So that cosine thing makes me think that this is probably sometimes positive, sometimes negative. I don't exactly know why it's over 2, but whatever. So I'm going to start off with an inequality. So I'm going to actually look at the absolute value of this thing. So the absolute value of cosine of n over 2 is less than or equal to 1. And because that's the case, I know that I can divide through by n squared plus 4n, which is positive, and that'll give me this relationship. So we have the cosine thing over n squared plus 4n is less than or equal to 1 over n squared plus 4n. And so the sum of each of those will have the same relationship. So we have the sum of the cosine thing over n squared plus 4n less than or equal to the sum of 1 over n squared plus 4n. So if you've gotten to this point in the video, or if you're trying this problem, you definitely know that that converges. And so what I'm going to do is I'm not going to prove it, I'm just going to kind of assert it in my proof. So I'm going to write, since the sum of 1 over n squared plus 4n converges, and I want to say why it converges. So if I were going to do the work, I would limit compare this thing to 1 over n squared. So I'm just going to say that by limit comparison to the sum of 1 over n squared, which is a convergent p-series. So I then know that the sum of the absolute value of cosine of, that should be n over 2, not 2 over n, converges over n squared plus 4n, converges by direct comparison. So far so good, but that's not the original series. That's the absolute value of the original series, but that's a valid thing to do. So what we actually just showed is that the original series that we were given converges absolutely. So in this case, we don't know that it's always strictly alternating, so it's not good enough to just say like alternate, decrease in magnitude, limit of 0. Instead, we looked at the absolute value of it. The absolute value of the thing converges, and therefore the whole thing converges, and in fact converges absolutely. All right, let's take a look at another problem. So we have sum from 1 to infinity of n factorial over e to the n squared. So I see a factorial, so I'm going to use the ratio test and see what happens. So it's the limit as n approaches infinity of the absolute value of the n plus first term, so I'm going to replace every n I see with n plus 1. So quantity n plus 1 factorial over e to the quantity n plus 1 squared times the reciprocal of the original, so times e to the n squared over n factorial. Okay, so it's limit. We can drop the absolute value because everything's positive. N plus 1 factorial over n factorial gives us an n plus 1. And then what I'm going to do is I'm actually going to, so it's like you could say it's e to the n squared minus the quantity n plus 1 squared, right? When you combine, you subtract exponents. But what I'm going to do instead is I'm going to actually bring the e to the n squared into the denominator as e to the negative n squared and combine down there. So that's going to leave me with e to the quantity n plus 1 squared minus n squared. And then I'm going to simplify that, right? So quantity n plus 1 squared is n squared plus 2n plus 1. So I'm going to do that, and then subtract off the n squared. So n plus 1, e to the, all that's left is 2n plus 1. If we go to infinity, you could use L'Hopital's rule, or you can just look at it. That's definitely going to give us 0, and 0 is less than 1. And so we know that the original series that we were given converges by the ratio test. All right, let's take a look at another problem now. So we've got the sum from 1 to infinity of n squared plus 1 over 5 to the n. This feels really similar to a problem that we've already done at some point. And on that problem, my inclination is to break it apart and do two separate integrals, show that they both converge. Two separate series tests, show that they both converge, and then sum them up. But just like on that problem, it's actually easier to do the ratio test, so I'm going to do the ratio test. So it's going to be the limit as n approaches infinity of the n plus first term, so all the n's become n plus 1's, like this, and then times the reciprocal of the original. And then we want the limit to infinity, so the 5 to the n and the 5 to the n plus 1 cancel, and we're left with the limit as n approaches infinity of n plus 1 squared plus 1 over 5 times n squared plus 1. And that's, a quadratic over quadratic, so ratio of the coefficients, or you can use L'Hopital's or however you want to do it. That limit is going to be 1/5, and we know that 1/5 is less than 1, and so we can say that the series we were given converges by the ratio test. All right, let's take a look at another one. So we want the sum from 1 to infinity of n times natural log of n over n plus 1 cubed. So I look at that and I think if I try the ratio test, I'm probably going to just get 1, so that doesn't seem efficient. I think I could integrate that. It looks like something that we could definitely integrate. But I think what I'm going to try to do is find a series to compare it to. And then I might need to do something to see if that series converges, but let's just see what we can work out. So I'm going to start off with denominators. So n plus 1 cubed, definitely bigger than n cubed. So let's flip it and change the relationship. All right, so we have this. Multiplied by n, so I'm just kind of like rebuilding the original series on the left-hand side and seeing what happens on the right-hand side. We have this, and then I'm just going to simplify it this step. So far we have that we're less than 1 over n squared, which is good because 1 over n squared definitely converges. Now I need to multiply in a natural log of n, which kind of makes the right-hand side a little worse. So I have natural log of n over n squared. Okay, so that means that we can compare the summations. So this isn't really a problem, it's just now I have to show that this series, the natural log of n over n squared, converges, because if it doesn't converge, then something went wrong somewhere, or this is just not a useful comparison. So let's see, I'm going to use the integral test on this. So I'm ending up using the integral test anyway. So f of x is the natural log of x over x squared. All right, so that is definitely continuous. It is definitely positive, because remember, we're going from 1 to infinity. And then I did the work separately, but this turns out to be decreasing when x is greater than or equal to 2. So we're looking for integers, so it's not actually 2, but greater than or equal to 2 definitely works. So now I'm going to try to integrate. So it looks like integration by parts to me, so I'm going to choose to integrate this. I need a u and a dv. So I'm going to say u is the natural log of x because I'd rather take the derivative of that, and then dv is whatever's left over, so 1 over x squared dx. So du is 1 over x dx, and v is negative 1 over x, and then that'll be uv, and then minus the integral of v du, so that's minus the integral of negative 1 over x squared, so plus the integral of 1 over x squared dx, and that we can integrate. So I'm just doing an indefinite integral, so I don't have to worry about writing the bounds every time, and it's also an improper integral. So now what I'm going to do is my improper integral. Ooh, don't forget plus c. Improper integral from 2 to infinity of this is the limit as b approaches infinity of substitute b into the antiderivative, and then minus what we get when we substitute, I guess I should have substituted 2, but I substituted 1, which is actually, I mean, that's a mistake, but I'm going to go with it anyway. So it should actually be minus, negative natural log of 2 over 2, and then minus 1/2. The key thing is that it's finite, so I'm not going to actually correct that because we're like 50 minutes in, and we don't need to watch that happen. But we got a finite value, and so we can say that this series converges by the integral test, and since this converges, and we know that the series we're actually dealing with is less than this, we can say that the series we were given converges by direct comparison. So that one's a little tricky because we had to either integrate the initial thing, which I'm confident you can do integration by parts on, but it seemed like it'd be really gross. So instead I found a series to compare it to, and I used the integral test on that, and then I direct compared based on that convergence. So sometimes you have to do things like that. All right, let's take a look at another problem. So we're going to go from 1 to infinity of... Oh, nope, we just did that one. Sorry. Let's look at this one. We're going to go from 1 to infinity of the arctan of n over n root n. Okay, so this one, it's a really good idea to know what arctan does as you go to infinity, and if you think about it, you know that it's always between negative pi over 2 and pi over 2, and if you go to infinity, it's pi over 2. So I know right away that arctan of n is less than pi over 2. And so that'll let me set up an inequality. I'm going to divide through by n root n, which is n to the 3/2. So I get this, and then that means the summations have the same relationship. And so it looks like we're going to use direct comparison. I factored out the pi over 2 there. So now I can just say, since pi over 2, the sum of 1 over n to the 3/2 converges, which we know because it's p-series with p equal to 3/2, we know that this series converges by direct comparison. All right, so that one wasn't so bad. Let's take a look at another one. I'm going to go from 1 to infinity of 5 to the n over 3 to the n plus 4 to the n. So this seems like 5 to the n grows faster than both of those functions. So what I'm going to do is I'm going to take the limit to infinity and see what happens. So we're going to try to use the nth term test. For a limit like this, what I usually do is divide through by the highest powered thing in the denominator, which in this case is 4 to the n. So I'm going to divide everything I see by 4 to the n, which gives me 5/4 to the n over 3/4 to the n plus 1. So if you think about it, as n goes to infinity, the numerator thing, 5/4 to the n, goes to infinity, because that's greater than 1. 3/4 to the n goes to 0, so we end up with infinity over 1, or just infinity, which means that overall we can say that the series diverges by the nth term test. All right, let's take a look at one more problem. So this one's actually kind of weird because you might not initially have any sense of how to do it. So we're going from 2 to infinity of 1 over the natural log of n to the natural log of n, which is very strange. So I'm going to speculate that this is probably, not the reciprocal, but natural log of n to the natural log of n. I think eventually is probably bigger than n squared. Because like the exponent on the left-hand side is going to go to infinity, and things to the infinity power are probably bigger than things to the second power. So let's see if we can work out if that's true or not. So I'm basically going to try to solve this inequality first. So I'm going to do that by taking the natural log of both sides, which it just seems like too many natural logs, but it's going to help us out. So this should still be true. And then exponents become coefficients, so I'm going to bring down the natural log on the left-hand side and the 2 on the right-hand side. So this problem feels different, I guess, from the previous ones that we've done. You can divide out a natural log of n. So we get natural log of n is greater than 2, which you kind of like think about it, you know eventually that's going to happen, but you can actually exponentiate and get that means that the natural log of n is greater than e squared. And you can exponentiate again. That means that n must be greater than e to the second, which is just huge. I think it's not like enormous, but it's like 1,618-ish. So it's very large. So now what I'm going to do is go back and actually do the problem. So I'm going to say that for n greater than e to the e squared, the natural log of n to the natural log of n is greater than n squared. And now I can take reciprocals, and it's going to swap the relationship, which is exactly what I wanted. So at this point, we know that this thing converges. So our summations have the same relationship. So we have this. And now we can just say that this thing converges. So I'm going to say since 1 over n squared converges with p equals 2, the sum of natural log of n, 1 over natural log of n to the natural log of n converges by direct comparison. All right, that's the end of me doing these. If you made it this far, I hope you found this really helpful, and good luck.